Okay. Hello, everyone. We hope you had a great spring break, and we welcome you back from the spring break. And I hope all of you enjoyed your time. We really missed you a lot during the break for a couple of weeks. And even though when you come back from spring break, sometimes you don't remember much, but don't worry, we have all our lecturers, all our TAs, and all the staff here. So soon we'll be doing some great work. So now let me hand it over to Rachel, who will have some announcements, and then we'll go to Amir, who will start us after the spring break, and hopefully we'll have some good time learning about quantum computation. So over to you, Rachel.
Cool. Thank you, Rahul. We invited Rahul to help welcome everyone back from break. He's one of the teaching assistants, if you haven't had a chance to meet him yet. But we are seriously so happy to see everyone back. I personally really excited. It's going to be a great few more lectures, and I hope you also had a relaxing spring break, enjoyed a few weeks just to process everything you've learned this semester. So again, obviously we have lecture today, and then labs will also kick off again this week. So we're back to a regular schedule. Believe it or not, we only have 4 more lectures left, including this one. So the last day of class, as a reminder, is May 9th. We will end with, I know, lots of sad comments in the chat. I'm also really sad that this is coming to an end. But we'll end on the last day with a really fun, interesting panel with guest lecturers from the Qubit by Qubit Advisory Board. So some of the leading names in quantum computing, university faculty members and things like that. So look forward to that. Again, please attend your lab sections this week. We'll be taking attendance as always. And just a few more things related to the course coming to an end. So the last homework assignment, homework 21, which is due tonight at midnight Eastern time, was just to submit your name, how you would like it printed on your certificate of completion for the course. So if you have not submitted that yet, which I know many of you have not, please jump over to Canvas. Just submit your name. It's really, really simple. We want to make sure we spell it correctly, we get the right symbols, have it represented the way you would like it represented to share as a credential for successful completion of the course. It's also worth points as a homework assignment. So again, please, please, please do submit that. To get your certificate, you need a 60% or above in the course. So if you haven't recently checked your grade on Canvas, please go into the grade section and confirm that you're passing. You can revisit the course grading policy in the student handbook, which is also posted on Canvas if needed. But we really want to work with all of you. We know students have worked really hard the last 8 months to succeed in the course. So if you're struggling or if you're behind, please do email us. We'll work with you on a plan to make sure you can pass. And just final announcement here is that there will be a homework assignment this week. There will be a homework assignment next week, and then we'll be done with homework for the remainder of the course. So your last assignment will be due on May 2nd to give us a full week to reconcile grades in order to get everyone their certificate. So let us know if you have any questions. Again, we're super excited to see so many of you back after the break and hope you enjoy Amir's next few lectures.
Amazing. Hi, everyone. It's great to be back from break. And my name is Amir, and today I'll be talking about quantum hardware. So we can skip through announcements. So over the course of the next 2 lectures, we will be talking about quantum hardware. Specifically, this lecture, we're going to be talking about the conditions and metrics that we need for building a quantum computer. Again, this is something that I will emphasize throughout this lecture, but so far, the parts of quantum computing that we've discussed treat the quantum computer itself, the physical computer, as an abstract, perfect machine. But now today we will be talking about what goes into building this machine, namely what systems can be actually used as a quantum computer. And also what are the criteria? How can we compare the different quantum processors that we built to see, first of all, if we're making improvements, and also to see which one's better for use for quantum computing in general. And next lecture, we'll talk about the quantum hardware implementations. So what physical systems can we actually use for building these quantum computers that I'm going to lay out for you today. So there are different ways to build qubits and quantum processors, and that's what we will be covering in the next lecture of this 2-lecture series. So we've been getting these questions throughout the course pretty much, and Akshay has done a great job of compiling a few of these. So the first question is, are the different qubit types meant for different applications? We will see that in the next lecture when we talk about different qubit technologies. Are electrons and photons qubits? Can they be qubits? We will talk about the conditions that our quantum processor and our qubit technology needs to satisfy to actually be able to be used for quantum computing. And then we can think whether electrons or photons by themselves can be used as a qubit or not. How are gates physically applied to qubits? So that's a great question. Again, we will be discussing that more in the following lecture because it's different from technology to technology, but I will be hinting at a few possibilities during this lecture. Is the Bloch sphere real? We've been talking, whenever we talk about qubits, so far in the course we've drawn a Bloch sphere, but is the Bloch sphere an abstract picture, or is it actually something that's real and physical? We will see. And then what does it look like physically when we entangle qubits? How entanglement is actually implemented? And again, that is something that we will discuss throughout this lecture a little bit, but mostly during the next lecture when we talk about the actual different implementations. So with that, again, let's start from the highest level possible. The goal that we have with quantum computing is to be able to obtain some form of a speed up over the best classical technology using our quantum algorithms. So the quantum algorithms that we've introduced so far in the course are Deutsch-Jozsa, Shor's algorithm, Grover search, which we talked about in detail. And of course, we're going to see near-term algorithms in 2 lectures from now. And actually, we will discuss throughout this lecture and the next one, why do we need near-term algorithms? What's different between these near-term algorithms and Grover search, Shor's algorithm, and Deutsch-Jozsa. So if we look at the quantum stack, now at the very high level up here, that's where the end user and domain expert sits. So the top of the stack is reserved for people who might not have any idea of how a quantum computer actually works, or what is the source of a quantum algorithm speedup. Then a layer below that, namely here, and I said that I'm drawing with black on black. We talk about quantum algorithms and what are different ways of actually, take the high level problem that we have and come up with a way or set of instructions for our quantum computer. But what we will be talking about today is at the very, very bottom of the quantum stack, namely where quantum hardware sits. So that the quantum hardware is a platform that actually performs the quantum computing, all those circuits, all those gates that we've talked about so far in the course. Now we actually have to physically implement them on an actual computer. And we're going to see how that's done and what constitutes quantum hardware, which is required to actually, gain and achieve all these amazing speedups that we've talked about. So what do we need for running quantum algorithms? Because that's the end goal, and we want to work towards that end goal. Well, for one, we need many qubits. So far, every time we've talked about quantum circuits or quantum algorithms, we've assumed that we have access to a lot of qubits. In fact, we've never considered the number of qubits to be a restriction. And of course, in reality, the largest processors that we have available today at least publicly known available today, all have less than 100 qubits. So the number of qubits is something that we need to be mindful of, at least in the next 5 to 10 years. Now, when we've talked about our qubits so far, we've assumed that they don't have any errors. They're perfect qubits, whereas that's not necessarily the case. And throughout this lecture, we're going to be talking about different modes of error for a quantum computer, which is a little bit more complicated than classical computers. So for running algorithms, we either want qubits with no noise or error, or we want a way to be able to correct for those errors, which we call error correction, or in this case, error corrected qubits. And of course, going back to the resources that we've talked about being required for quantum computing, we'll need a way to create superposition, quantum entanglement, and quantum interference between our quantum states to be able to actually achieve these speedups that we've talked about so far. So what are the properties of a quantum computer? This is at a high level, and we'll get a little bit more specific. Of course, we want enough qubits to run algorithms. Now, what is enough depends on different problems that you're trying to tackle and different algorithms that you want to implement. But let's just say, for now, as many as we want would be enough. And of course, we need a way to fix errors if they occur. So again, going back to the point that I made, that in the assumptions that we've made so far, talking about quantum algorithms without actually, before talking about quantum hardware, we've assumed that we have access to perfect operations and perfect qubits. And ideally, that is something that we want to strive for. Now, since in real life, it's really hard to make anything be perfect, we want a way to actually correct errors once they happen, assuming that errors will happen. Then we want a set of gates that are universal. Again, this goes back to the notion of universality that we've discussed throughout the class. We want to be able to have the tools, rather, to implement any algorithm that we want on our quantum hardware. And of course, that set of gates are universal gates. And finally, we want the capability to read out the state at the end of the algorithm. So if we take a couple of steps back to before spring break, which sounds like an eternity ago, I know, but when we talked about Grover's algorithm, we started by preparing the states initializing all the qubits to 0, and then we perform a set of gates for the algorithm. In this case, for Grover's algorithm, that set of gates look like this. We apply Hadamard's first to all the qubits, and then the oracle operator, and then the entangling operator, or the reversion around the mean operator. And after we repeat these for enough times, after we're done executing our quantum algorithm, or the quantum circuit for the algorithm, rather, we would like to measure the state of the quantum computer to see what output we get. So the final criteria that we want here, at least at the high level, is a capability to read out the state at the end of the algorithm. Now, there are different quantum hardware platforms, which we will discuss more during the next lecture. So right now, one of the most popular platform technologies are these superconducting qubits that I'm showing here. And that begs a question. So what will be the equivalent of a transistor, which is the building block of a classical computer, for quantum computers? Or rather, what will be the quantum transistor in the future? And also, in perspective, are we in the quantum vacuum tube era of quantum computing, or where are we exactly? These are all open questions that we're actively trying to answer. So that being said, next lecture, we are going to be talking about 4 different modalities for quantum computing, 4 candidate platforms that could be used, or we think that could be used for realizing a quantum computer in the next, let's say, 5, 10, or 15 years. So the first one, of course, is superconducting qubits. That's what my research is focused on. We'll also be talking about trapped ions, diamond NV centers, and photonics, or systems that use photons as the building block for quantum computing. And again, we will see exactly in detail what do these platforms entail, how do we operate them, what do the physical qubits look like. So the one spoiler that I want to give you is that the physical qubits actually don't look like the block sphere that I have here. This is just an abstraction that we use to represent the state of a qubit. Now the physical qubits, look very differently. In this case, for example, in superconducting qubits, there are these superconducting circuits which have essentially a capacitor pad and a small junction, and that somehow behaves like an artificial atom. Or in diamond NV centers, you have a diamond lattice, which is all made out of carbons. You have a nitrogen next to a lattice vacancy, an empty spot in the lattice, and turns out the electrons that hang out in this vacancy have, can be used as a qubit. Now, we will be talking about these questions and these platforms in more detail next lecture. I just want to give you guys a teaser for what's to come. So let's take a step back before we talk about the state of things today and what how difficult it is, or what criteria do we need to satisfy if we're actually building these quantum hardware, and talk about the history of quantum computing in general. So the idea of quantum computing, as you probably all know by now, was introduced 40 years ago by Richard Feynman, where he proposed using a controlled quantum system, or a quantum processor, you can think of it, or quantum hardware, for simulating the behavior of some quantum system of interest. Now, fast forward to 1994, Peter Shor showed that he can use a quantum computer to factorize large integers efficiently, and two years later, in 1996, Grover demonstrated Grover's search algorithm, which we talked about. Now, it wasn't until 1998 where we had the first experimental demonstration of a quantum algorithm. So this means that we actually took a quantum algorithm. In this case, of course, it was a 2-qubit algorithm, which is nothing too crazy, but yet, we were able to actually demonstrate that we can perform quantum computing using a quantum system. So in this case, the implementation was done on an NMR quantum computer by Ike Chuang, who's a professor now at MIT. And this was the first time that the idea of quantum computing went from an abstract notion to something that could be done in reality. Now, fast forward, many years. Of course, there's been a lot of progress here that I'm not detailing, but we were able to demonstrate, quantum processors with few qubits and error detection. So the capability of detecting an error, not correcting necessarily, but just detecting if an error has happened on our qubits during our computation. And of course, then we got cloud-based quantum computing when IBM put their devices and gave public access through the cloud to their superconducting quantum devices. And of course, we had the demonstration for quantum supremacy, or you can think of it as a form of quantum advantage, in 2019 using one of these superconducting quantum processors. So you can see that the field's come a long way. There has been a great deal of exploration and advancement in terms of the theory and the algorithms, although there is still much to be done. But the hardware is slowly catching up. And building quantum hardware is very difficult. We will discuss why that's the case exactly a little bit this lecture. But now the question that I want to answer throughout this lecture is, what criteria does a system need to have so that we would be able to use it as a quantum computer? Now, before we get there, why can't we run Grover's algorithm on a meaningful data set today? Well, first of all, we don't have enough qubits, as I mentioned earlier. The most number of qubits that we have on a processor that we know of, at least today, are less than 100. And those qubits are noisy qubits. They're not error corrected, nor they're error free. And that makes things very difficult. And to make matters even worse, or rather more challenging, the gates that we use to operate between these qubits, think like your X gate, your Pauli gates, or your C naughts, they're not perfect. They're pretty good, but they're not perfect, and they need to be improved before we can actually think of running one of these large scale algorithms like Grover's and Shor's on quantum hardware. So the learning objectives for today are, so far we've assumed a perfect quantum computer. How do we decide what systems are capable of performing quantum computation? And also, the second question that I want to address today is, how do we decide how good is a given quantum computer? How can I compare and contrast my quantum processors and decide if they're suitable for certain tasks or not? So with that, the first topic I want to discuss with you is DiVincenzo's criteria. So DiVincenzo's criteria is a set of 5 basic conditions for a physical realization of a quantum computer. There are usually 2 extra ones for quantum communication, but we're not going to worry about those. This is just for quantum computation. So the TLDR, or the layman version of what DiVincenzo's criteria are basically, what properties does a quantum computer or quantum processor need to have in order for it to be useful for quantum computing. The first criteria is that we want a scalable physical system with well-characterized qubits. So let's take this part by part. The first part is scalable, meaning that we want to be able to add as many qubits as we want to our processor without there being any physical or technological, technological, of course, is different, but without being any impediments from the laws of physics. Now, the way that I can think about it is, every qubit is a piece of puzzle is a piece in a larger puzzle. And we want to be able to basically have as large of a puzzle as we want in order to be able to solve the problems that we want to solve. So that's what I mean by scalable. Now, I say qubits. So a qubit is, again, a 2-level system. And if I want to show this, actually, we have 2 levels. I can call one of them 1, the other one 0. So I want a system that has a well-characterized level structure such that I can actually use, 2 of its levels as a qubit. So now in nature, and this is something that we will see more in the next lecture,
Amar, could I jump in with a quick question? So what do you mean by well-characterized here?
I was just about to get to that.
Sorry.
All good. So in nature, the systems that are available usually have many, many energy levels, and that's just the property of natural systems. But now what we want from these systems is, I want a system that has, that I can isolate 2 of its levels. I would know exactly what the distance between is, such that I can drive transitions between 0 and 1. And I can reproduce this basically as much as I want. So the meaning of well-characterized, as the question that Akshay brought up, means that I want to understand the properties of the system well enough such that I can engineer gates and operations, and also I can replicate the system many times because I want many qubits. Again, there's no trick parts here. The main takeaway is that, I want a system where I understand the properties well enough that I can build as many qubits as I want. That's all. So yeah, and maybe let me just write a note about well-characterized on my slides. So we mean that we have a good grasp of the properties of the system. And the example that I want to emphasize here is the distance, or the energy difference between 0 and 1. So That's all there is to it. The next criteria is that I want the ability to initialize the state of the qubits. So if you remember, when we've talked about these algorithms that we've had or the circuits that we've had in the throughout the course of the semester, we usually start with the qubits initialized to the 1 state, or sorry, the 0 state. And I want to be able to basically initialize, have the qubits all start in the 0 state with, high certainty before I start running my algorithm. So I want to be able to know exactly where I'm starting from in order to be able to have a successful quantum computing sequence. One way of thinking about it is that you could think of this as glow sticks and how I can initialize them to, kind of flash the color that they are by breaking them. So we want something like that. We want a sequence of operation or a way to be able to actually have the qubit state be at 0, or whatever state we want it to when we're starting our quantum algorithm. Now, the next criteria is that we want a long relevant, and this decoherence time is a concept that we will be talking about a lot during this lecture, but we want a long relevant decoherence time, which is much longer than the gate operation time. Now, decoherence time is the amount of time that the qubit preserves its quantum properties, or you can think of it as the amount of time that the qubit preserves quantum information. Now, one good way of thinking about it is, you can think of your qubit as a hot cup of coffee, and ideally you want to drink your coffee before it gets cold. So now the time that it takes for your coffee to get cold is the equivalent of decoherence time in this picture, and you want to be able to drink your coffee before that. So one way of course extending this decoherence time is to put it in one of these thermal flasks, and actually we will see that this analogy holds well when we're talking about the physical system as well, in the second part of this lecture. But again, the message of this third criteria, this third DiVincenzo criteria, is that we want to be able to do all of our quantum gates, all the quantum gates required for a quantum algorithm during the time for which the qubits still have their quantum properties. Again, when you put it that way, when you say that way out loud, it kind of sounds intuitive. You want to be able to do all your quantum computing while your system is still quantum. Again, the way that we quantify this time that the system is quantum is using this decoherence time that we will see again later on in the lecture again. So we want this decoherence time to be longer than the amount of time that it takes for us to execute our quantum program. So that was the third DiVincenzo criteria. Now, the fourth one is that we want a universal set of quantum gates. This one hopefully should be fairly clear to you all by now, since we've talked about the concept of universality throughout the course. But another intuitive way of thinking about it is I can think of it as your set of gates as a toolbox, and you want to be able to have the tools to fix any problem, and that is essentially, that would mean a universal set. Now, in quantum computing, a universal set of gates is Hadamard, the T gate, and just for reference, the T gate is it's the square root of the S gate, and the S gate is a square root of the Z gate. Or you can think of this as a rotation on the block sphere by around the Z axis by pi over 4. So, or this is R of Z by pi over 4. So a universal set of gates for quantum computing includes the Hadamard gate, the T gate, and let's say C naught. Of course, there are different universal sets that you can come up with, but this is just an example of one. And the claim here is that if you can have these 3 gates, very well, very accurately, you can run any quantum algorithm that your heart desires by decomposing the gates and the sequence of operation in your algorithm to these sets of gates, to a combination of these gates. And finally, we want a qubit-specific measurement capability. So again, this goes back to, at the end of our quantum algorithm, we want to be able to measure the state of the quantum system to be able to get the correct answer out of the algorithm. And for that, we need a way to measure the qubits. And that is what the 5th DiVincenzo criteria asks for. Just asks for us to have a specific way of measuring the state of the qubit after we're done running the algorithm sequence. So with that, let's take a quick 10-minute break. I understand that this part of the lecture was a little bit shorter, that the next part will be a little bit longer. And I'd be happy to answer questions after the break.
So like 141, Amir, or 241, sorry.
You mean bread and butterflies?
Oh, yes, of course. Hmm?
Okay, everyone. I think it's time to get started with the lecture again. Before I answer questions, though, I would like to just do a quick recap of the DiVincenzo criteria that we've discussed so far. So first, we said that the first criteria we want our quantum device, our quantum processor, to satisfy is that we want it to be a scalable two-level quantum system. I also had the word characterized in there, well characterized rather. So the reason why we want it to be scalable is because we want our quantum processor to be able to have as many qubits as we need for our quantum computing task. I mean, in general, the more qubits, the better, but we don't want there to be a physical limitation, a limit imposed by the laws of physics as to how many qubits we can have. The reason why we need a two-level quantum system is because we use the two-level quantum systems as qubits for quantum computing. Now, what I meant by well-characterized earlier is that we need to understand the properties of this quantum system well enough such that we can control the transitions or changes from the 0 state to the 1 state back and forth of each qubit. And of course, that is a cornerstone for being able to do accurate quantum gates and operations, which are required for quantum computing. The next criteria that we talked about, the second criteria, is that we need to be able to initialize the state of our quantum bits or qubits in the system prior to starting our quantum computing to what we want. In general, the default assumption is that we start with all the qubits in the 0 state, and we want to be able to do that with high certainty before we get started with our quantum computing procedure. Then we want long relevant decoherence times. And basically what that means is that we want our system to actually be quantum or have quantum properties while we're executing the gates required for quantum computing. And I think when you, again, putting it like framing it that way makes it sound almost intuitive. In order to be able to do quantum computing, we need a quantum system that is capable of superposition, interference, and entanglement. Next, we want a universal set of gates, meaning that we want to have the tools necessary to execute any quantum circuit that we want. And finally, we want to be able to efficiently measure the state of our quantum system after we're done executing the quantum circuit that we choose. And again, that is the part that at the end of every quantum circuit for any quantum algorithm, we want to be able to read out the quantum state such that we can get the answer. Now, some of the platforms that we will discuss in the future lectures are, of course, trapped ions, superconducting qubits. We're not going to be talking about trapped electrons, but again, that's another platform, trapped electrons in silicon for photonics, which we will discuss during the next lecture. So now with that, Rachel, could you please tell me what were some of the questions that were asked during the break?
Yep. Yeah, Amir, thanks for the great summary. So a few more specific questions. A student was asking about the difference between logical and physical qubits.
Mm-hmm. So that's a great question. And I don't think I use the term logical qubits at all this lecture, but the difference is, so when we talk about qubits right now, we're talking about physical qubits. So these are the physical building blocks, physical transistors of our quantum system. Now, the problem with these physical qubits is that they're noisy for reasons that actually we're going to see now. So they're error prone. So what we can do is that we can combine many of these physical qubits using some quantum circuit, some procedure called error correction, in order to realize one perfect or error-free log. Now this is called a logical qubit. So that is the difference. Essentially, physical qubits are like the number of qubits that we physically have printed on our chip, let's say, and logical qubits is like the way that we combine them to realize one error-corrected perfect qubit. There are ways to do that. That's a whole field of quantum error correction, but we're not going to dive into it because it's a little bit more complicated than we would like to go in terms of the content. Now, for quantum computing, for quantum algorithms, everything that we've talked about so far, we've assumed logical qubits essentially. But what we have in reality are physical qubits.
All right, a related question. So a lot of our students have probably heard about D-Wave, a company that's active in the quantum computing space. So they said, what about D-Wave computers and what is annealing?
Yeah, so annealing is a different, so quantum annealing or adiabatic quantum computing is a different model for quantum computing than the circuit model that we're discussing so far. So the way that quantum annealing works is that you prepare a quantum state that is associated with a well-known energy, with a well-known problem, and then you slowly change the problem. And if you do this process slow enough, the correct answer that you had to the easy known problem will also be will remain the correct answer for the difficult problem that you're trying to solve. So that's the premise behind quantum annealing. And again, I simplified things a lot. There are a lot more technical details, but let's not worry about those for now. Now, D-Wave specifically, they print thousands of qubits, superconducting qubits, in fact, on their chips. But of course, it's questionable whether they satisfy some of these DiVincenzo criteria or not. For example, the coherence times on D-Wave's qubits are fairly low. They're, let's say, of order of hundreds of nanoseconds. And again, that number in and of itself might sound too short, but doesn't mean it necessarily is. But anyways, they're like of order of hundreds of nanoseconds when the programs that they try to execute take way longer. So at least to the best of my knowledge, and again, please feel free to correct me if you know more or give me the appropriate references. But to the best of my knowledge so far, based on what they've advertised, the quantum sequences that they run take much, much longer than their coherence time, than their qubit coherence times. Which of course, then begs the question of whether, the whole process is quantum or, whether, the majority of the process is actually just classical annealing rather than quantum annealing. Of course, there are a lot of open questions, a lot of academic debates about D-Wave, so I don't want to go down that rabbit hole necessarily.
Well, in the second half of the lecture, we'll talk a little bit more about how to compare different types of technologies. So yeah, we can come back to that. Cool. So we've said several times that we can't run Grovers and Shors on the hardware we have today. How many qubits would we need to run these advanced algorithms?
Yeah, that's a great question. So again, here we're talking about, of course, physical qubits to distinguish it from logical qubits, where we talked about earlier. That's still an active area of research because we're nowhere close to actually having the capability to run these algorithms. But some estimates that I've seen for shorts at least, put it in the on the order of 100,000 to 1,000,000 physical qubits at the very least, conservatively, in order to be able to run Shor's for a meaningful number that you can't do classically. So the answer is a lot of qubits, and actually probably the accurate estimate is even a little bit higher than that. But that's just to give you a rough idea of where we need to be versus where we are right now, which is, let's say, 100 qubits optimistically.
So we need everyone in this class to go into quantum computing.
Yeah, and actually, I mean, that goes to highlight the importance of the work that is being done on quantum hardware. Because again, without better hardware, there's no way we can run these quantum algorithms. And again, there are quantum algorithms where we know could be used to solve some very important problems, like quantum simulation for optimizing the fertilization generation process, which consumes about 1% of the world energy consumption every year. But we have an idea of how to solve these problems. We just don't have the device yet, and actually building the device is very difficult. So that is the importance of quantum hardware, in my opinion.
Cool. Can you clarify one more time what you mean by scalable?
Yeah, so scalable, and I try to hint at it again in my review of these criteria, but just scalable means that there shouldn't be any barriers imposed by the laws of physics into for building a processor that has millions to trillions of qubits. Of course, figuring out the technology is a different question, but something that we've seen based on just the growth in the classical computing industry is that we are pretty good at engineering larger and larger systems once we figure out the how things work.
Awesome. And then let's wrap up with 3 questions related to decoherence. So do qubits in states 0 and 1 have different decoherence times? What's the highest decoherence time yet? And then most importantly, probably, how do you increase decoherence time?
Yeah, so we'll actually address this in, I think, less than five slides, or maybe 5 slides. But to answer your question, so of course, decoherence time matters not at the 0 or the 1 state, but when you're in a superposition of both. So you can think of decoherence time as a metric between 0 and 1, not necessarily at 0 and 1. So, and again, we will discuss why that's the case exactly, but just for now, I think that's a good answer. The second question is, what is the longest decoherence time? It'll depend a lot on the platform, honestly. For superconducting qubits, which is my area of research, there's actually a very recent paper, as of I think I would say like less than a month, that reported a decoherence time of larger than a millisecond. Now you might think, oh, a millisecond is a short amount of time. But keep in mind that the gate time for these superconducting qubits are of order of 10 to 100 nanosecond. So the decoherence time that we have, or that that they've achieved on the system, is much longer than the gate time, which is the metric that we should really be looking at. Of course, trapped ion systems, and again, we will discuss these later. Like next lecture, we're gonna have an expert actually talk about these. But trapped ion systems, regularly have decoherence times of order of milliseconds to seconds, but of course the gates are slower there. So I think this is a kind of it's a great sneak peek for our discussion in the next lecture about these different platforms, with of course the experts who are doing research on each of these platforms. And what was the third question?
Just how do we increase decoherence time?
Oh, how do we increase decoherence? I mean, again, I will talk about this, but if you shield your qubit better from the environment, chances are you'll increase your decoherence time. And think of it again as the example of a coffee just sitting in a normal mug, which will eventually dissipate energy to the environment, versus a coffee in an isolated mug, which will kind of prevent the heat, the coffee heat, from going out to the environment.
Cool. That was it.
Okay, amazing. So yeah, with that, let's talk about what I like to call the quantum hardware spec sheet. Specifically, this is a term that I just made for this lecture, but what we're going to be talking about is what are the metrics that can tell us about the quality of our quantum hardware. So actually, before I tell you what these qualities are, I want you to look at these 3 quantum processors that I have here, and I'm going to start a poll, and I would like you to tell me which one do you think, make an educated guess, is a better quantum hardware. Again, they all have 5 qubits, they're all IBM superconducting qubits. And I have some properties down here below each, but of course, I don't expect you to know what any of these mean so far. So that being said, tell me which one's a better quantum processor. Hey, let's give it 30 more seconds so everyone can get an answer in. Okay, I think most participants managed to get something in. And yeah, it seems like the majority of you think option 1, and let me maybe change the color on my pen, is the best quantum processor out of the 3 options that I have laid out here. Okay, so let's see, we'll revisit this question again at the end of this lecture. And we'll see if your answers have changed or not. So the first concept that I want to draw your attention to is qubit relaxation. So the concept, the physical concept behind qubit relaxation is that physical systems tend to dump energy into their surroundings. And an example that is actually a favorite of Rachel's is that if you have a hot coffee sitting on your table, after some time, it will get cold. So in a sense, your coffee will dump its heat, which is a form of energy, into the surrounding environment. Now, qubits behave the same way. So what I've tried to hint at so far is that you can think of these qubits as systems that have two levels or more levels, but 2 levels that we care about. And I'm going to call the top one 1, because generally the level that has a higher energy is the 1 state, and the level that has a lower energy is the 0 state. And of course, the energy of 0 is less than the energy of 1. So if you just let your qubit sit, for a long time, it will decay to a lower energy state. So this means that if your qubit's in the 1 state, it'll dump some energy in the environment and actually go down to the 0 state, which has a lower energy. And again, if you want to think about it in terms of the coffee example, this is your qubit being in the coffee hot state, here in the 1 state, and then it goes in the coffee cold state by dissipating some energy into the environment. So that's what qubit relaxation is, basically. And of course, I think it's fairly clear how that could interfere with the quantum computing process that we want to do. Because again, when we initialize a qubit to a 1, let's say, when our qubit is in the 1 state for some part of the quantum computation that we have, we don't want it to actually drop down to 0. Well, so now what I stated is that the qubit state decays from 1 to 0 over time. And the way that we quantify that is with relaxation time, which is shown as this quantity T1. This is actually fairly universal way of showing this, not just for quantum computing systems, but throughout quantum physics. Now, the way that this happens is that the probability of measuring your qubit in 1, if you've initialized it in the 1 state, will decay exponentially in time. And the decay constant is this T1 that we're looking for. Now, the question that I want to ask you, and I want you to think about it for, let's say, 15 seconds, is how can I measure this T1? Is there a way for me to measure the T1? And think about it for like 15 seconds, and then I'll explain how we do it. Okay, so what about this? So I'm going to first talk about the suggested protocol, and then I'm going to show you like a circuit of how to do it. So what if, again, I have these two, the qubit, right? The two levels, 0 and 1, and I start from the 0 state because that's how I generally initialize my qubits. Then I excite my qubit using a pulse from the 0 state to the 1 state. So now my qubit's in the 1 state. And then I just measure the state of the qubit after some time for different times and see with what probability I get the qubit being in the 1 state versus the 0 state. Now, the circuit for this, if I were to draw a circuit, would look like starting from 0, applying an X gate, and then waiting for some time, and I'm going to call this time T. And then measuring the state of the qubit at different times. Now, of course, the more hardware way of writing it is that, again, I start with the 0 state, and then I apply a pulse. So this is a pulse. And in this case, I want to apply a rotation around, let's say, the x-axis with by pi degree by pi radians, which corresponds to the X gate that I have up there. And then I wait for some time, and then I measure. So these two, so this 1 and 2, are doing the exact same thing. One of them, I'm just actually drawing a pulse instead of a gate, which is an abstract thing. Okay, so if I do this for a superconducting qubit, here is what I end up with. And let me hopefully. Okay, let's try to go next on this. Here we go. Worked. So initially at time 0, when I measure, I'm completely in the 1 state. But as time goes on, as this time between when I applied this X gate, between when I initialize my qubit to the 0 state, to the 1 state, and when I measure the qubit state increases, I see that this probability drops down exponentially until until after a long time it actually reaches 0. And in this case, for the qubit that we measured in our lab, we get a T1 of 85 microseconds, which is a decent number in comparison. So that's how. Yeah, go for it, Akshay.
Getting a few questions in the chat. So could you clarify here what exactly you mean by a pulse? And what is it
okay,
like? What is it doing here?
Yeah, so a pulse does this. Again, I showed it up here earlier. It does this transition from 0 to 1. No, it's just zapping the system with enough energy to make it jump from the 0 state to the 1 state, and that's a pulse. And yeah, that's all it does. So you can either think of it as a pulse or an X gate, or a rotation around the x-axis of the Bloch sphere. Was that the only question?
Yeah.
Okay, amazing. So with that, let's go. So actually, before we jump to decoherence, let's talk about how to make things better. So we want to build qubits that are more isolated from the environment. In general, that's a good thing to accomplish, because in this case, of course, then our qubits will not dissipate energy to the environment as rapidly. And again, the example would be putting your hot coffee in an isolated mug, which will keep your coffee warm for a longer time. And we can do this in qubit land by either having better material or reducing different loss mechanisms. or different ways that your qubit can lose energy. And of course, one other way of making this possible is to make the transition from 1 to 0 more difficult. So you want to make it such that like when this, this is the 1 state, this is the 0 state, and your qubit, let's say, or your energy is in the 1 state, you want to make it such that based on the laws of physics, your system, your qubit, will have a harder time of actually dissipating energy and falling from the 1 state to the 0 state. And of course, this opens a whole can of worms when it comes to engineering these quantum systems, and it requires a decent bit of knowledge in physics to be able to accomplish these. But for example, this is how those superconducting qubits that achieve millisecond decoherence times and relaxation times actually did it. They just made it such that it's harder for your qubit to drop down from the 1 state to the 0 state. Now, the next concept I want to talk about is qubit decoherence. And quantum systems lose their coherence as a result of interacting with the environment. And that leads to the decoherence that we've talked about. And when quantum systems lose their coherence, or rather decohere, the superposition turns into a classical probability distribution. Now, if you remember from an example that we had earlier between a quantum superposition and a classical coin flip, you might remember that classical systems don't have the ability to interfere with one another, classical probability distributions, whereas quantum systems can quantum interfere, and that quantum interference leads to a whole set of speedups that are required for quantum computing. So overall, the reason why we want this decoherence time to be as long as possible is because we want to have the quantum properties that we need for classical computing for as long as possible, or sorry, for quantum computing as long as possible. Okay, I did this wrong. Again, the premise is that the qubit loses its quantum coherence over time, and the way that we quantify this is with T2. So this, in a similar way, where having a longer T1 is a good thing, means that it takes longer for the qubit to dissipate energy and drop from 1 to 0. Having a longer decoherence time is also a good thing. So longer decoherence time means that, or longer T2 means that you can have a sequence of quantum operations that take a longer time. Now, things get a little bit more complicated when it comes to T2 compared to T1. So when you're computing T2, this T2 takes contributions from 2 factors. First of all, relaxation affects your decoherence time, or your T2. But also dephasing, which is another concept, also contributes to this T2 number. So this is the relation that generally holds. 1 divided by T2 is equal to 1 divided by 2 times the relaxation time, or T1, plus 1 divided by T phi. And this T phi is the dephasing time. Now, the question that you might ask me now is, okay, how do we figure out what this T2 is? Well, we can do something called a Ramsey experiment, where we start with the qubit in the 0 state, but now instead of putting it fully to the 1 state, we put it in a superposition of 0 and 1, or you can think of it as on the equator of the Bloch sphere, by, in this case, applying a pi/2 pulse around the x-axis. So the pi/2 pulse around the x-axis brings a qubit from, and again, maybe I should draw a Bloch sphere up here. So this is the Bloch sphere. This is 0. This is 1. What this pi/2 pulse does is that it brings a qubit from all the way on the North Pole to the equator. So that's what Rx pi/2 does. So we bring the qubit on the equator now, and now we wait for some time, t, And then we, there are different things that we could apply, but let's say we apply the inverse pulse. So Rx minus pi over 2 to bring it back up there. Okay, so now the question that I want to ask you, and again, I want you to think about this for, let's say, 10, 15 seconds, is if nothing goes wrong, if we have a purely quantum system this whole time, after I apply the second pi over 2 pulse, what happens? Now, what if after I apply this first pi over 2, after I bring the system in a superposition, in a quantum superposition, then all of a sudden, because of reasons, my system becomes classical. Then what happens after I apply the second pulse? And then, of course, here I measure. Well, so if nothing goes wrong, if everything is quantum, then so this first pi over 2 brings a qubit on the equator, and then the second pi over 2 takes the system back, right? Back up to 0. And again, that's due to quantum interference, actually, because we're in a superposition of 0 and 1, and then when you apply the second one, the phases will, the one state will destructively interfere such that you go back to 0. Now, if this is a classical system, if this is a classical probability distribution, then after you apply the first pi over 2 pulse, you'll be in it's not a 50-50 superposition, but it will be similar to a coin toss. So you'll be in a 50-50 classical probability distribution. Now, the way that you can think about it, and we've encouraged you to think about it throughout the course, is what happens if you flip a coin once, which is, applying this first pi over 2 pulse, and then flip it again. Look, what are the probabilities of heads or tails during the second flip? Well, so since the second flip doesn't depend on the result of the second flip doesn't depend on the result of the first flip, then what you expect to get is that you expect to get 1 with half probability and 0 with half probability. And that's the difference between a quantum interference and if you have a classical distribution. Now, by varying the time here, we can see how we go from a purely quantum superposition to a classical superposition in time. How does that change? So that's the Ramsey experiment. And it looks something like this. So in this case, actually, the second pulse that we're applying is a plus pi over 2. So let me draw this again. So you apply 0 and Rx pi over 2. You let time pass. And you apply another Rx pi over 2. And the only difference here is in the purely quantum state, in the purely quantum regime, where everything is quantum, there's no decoherence, you'll end up in the 1 state instead of the 0 state. Now, based on this, you can see that this envelope is actually decaying. And it's decaying to, well, we don't have it here, but the value of 0.5. So if you wait for a very long time, if this t goes very long, you'll see that after applying the second pulse, the second, you can think of it as superposition creating pulse, or even a Hadamard, if that is better, you'll end up 50% up, 50% down, which means that things are completely classical. And actually, based on this decay rate, you can find out what this T phi is that I have here, and what this 2T1 is that I have here. And based on that, you can figure out what the T2 of your system is. So in this case, this qubit actually has a pretty decent T2. It is going to be roughly of order of 100 microseconds. And I was able to figure that out with this Ramsey experiment. Now, if you want a more comfortable picture, another way of thinking about this is just, starting with 0, applying a Hadamard, waiting for some time, and applying another Hadamard gate, and then measuring. So this version of things is equivalent to what I've described earlier, although usually in experiment, we just apply a rotation around one of the axes instead of a full Hadamard. Okay, if there are no questions about how to calculate, how to figure out what this decoherence time is. And again, the way that we figure it out is by seeing how our quantum computer, or how a qubit loses its ability for quantum interference in time. The way that we can make it better is, of course, to isolate the qubit better from the environment. Because the main reason that we experience decoherence is, that there's noise from the environment that is induced on the qubit, and that effectively destroys the quantum information or the quantum coherence of the qubit. And of course, so there are two ways of going about that. First of all, we can reduce the noise, the environment noise, the noise that is around in the environment. And the second way is that we can engineer our qubit such that it is less susceptible to environment noise. So there could be noise in the environment, but our qubit cares less. It's somehow more isolated from the environment. And of course, let's ignore this. This shouldn't be there. Now, let's talk about a real life research example from how can we improve these coherence times. So, a recent work that was published in August 2020 talks about the impact of ionizing radiation on superconducting qubit coherence. So, ionizing radiation can be, for example, the radioactivity of the concrete that's surrounding, or in this case, superconducting qubits, the Dilfridges around the qubit, or it could even be due to cosmic rays that come from outer space. Actually, in fact, there was another work as of last week that by Google that measured the effects of these cosmic rays on their quantum processors, and they're actually pretty major. Now, I'm going to share a video that is meant for, that explains, what this research is in layman's term. But, as you look at the author list, there might be two names here that are familiar. So, of course, one of them is mine. This is my first research project in grad school. And another one is Franz, who was back then an undergrad at MIT working with me and the postdoc on the team on this project. So with that, I want to share a video about this project with you, so you can see what research is actually like in quantum hardware, and also in improving these. Well, first of all, figuring out exactly what are the mechanisms that lead to decoherence, either again through dephasing or through relaxation, and how can we tackle them? How can we actually find a way to make our system less susceptible? Okay, I'll just make sure I'm sharing I'm sharing the sound. Amazing.
Hi, my name is Francisca Vasconcelos, and I'm a senior undergrad researcher working at the Engineering Quantum Systems group at MIT. This group is a lab within the MIT Research Laboratory for Electronics that focuses its research specifically on quantum computers. The difference between a quantum computer and, say, a computer that one of us uses is computing power and speed. There are certain types of algorithms which would take thousands of years to run on even the world's fastest supercomputer. However, there are also quantum versions of those algorithms that can be run on a quantum computer in solely a matter of minutes. At the moment, the group works a lot with 5-qubit samples. You can think about a 5-qubit sample as a single puzzle piece within a much larger 10,000-piece puzzle. Computers require millions of transistors in order to be useful, and we aim to eventually build a quantum computer with hundreds of thousands, if not millions of qubits, so as to perform even more powerful computations. A big challenge that quantum computers currently face is noise, and that's what a lot of the group's research currently focuses on. One of the current objectives of the lab is to reduce the amount of noise associated with each of these samples. This is so that when we put them together, we can have a working quantum computer. One of the hypotheses that we're trying to figure out is whether background radiation contributes to noise within our samples. So, how we're going to test this hypothesis is by first putting one of our samples in this special dilution refrigerator. This refrigerator cools down the inside temperature to close to absolute zero. We need to do this in order for the 5-qubit sample to operate. We are going to run 2 experiments simultaneously. The first is a control experiment in which we leave the fridge uncovered and exposed to all the background radiation. Every 10 minutes, we swap to our second experiment by lifting a shield of lead bricks to surround our fridge, reducing the radiation it sees by a factor of 10. We continuously swap between these two experiments every 10 minutes, lifting the shield up and down around our fridge. By measuring certain properties of our qubits, we can see if the qubit performance is hurt by the radiation. Through repeated measurement and statistical analysis, we hope to see that the lifetime of the qubits is reduced when the shield is down and they're exposed to radiation.
So with this data, right now what we see is that for our long-living qubits, the mean of the distributions actually do start moving apart from one another. So when the lead shield is down, we see a lower lifetime mean than when the lead shield's up. Also, we see that the distributions start to move apart from one another. Granted that we need more data at this point, but based on the measurements on the 5 qubits that we're making simultaneously, we anticipate that with better qubits and more data, we will see that canceling of background radiation will lead to an increase in the lifetime of the qubits.
So, in looking at the data from our experiments, there seems to be less noise in the qubit samples when we use lead bricks to protect them from radiation. This means that future full-scale quantum computers may require some sort of radiation protection. At the end of the day, with our research, we are trying to bring full-scale quantum computers a little closer to reality.
Yeah, and hopefully you'll remember that we saw this video earlier in the course in the first semester. And what I'm hoping is that now you appreciate it more and you have an understanding at least what roughly was happening in that video for the research that we were doing. Yeah, so again, that's an example of an active area of research. Something that people are looking into now is reducing the impact of cosmic rays from outer space, and also the background radiation in any room on the coherence time of these superconducting qubits. Now, let's talk a little bit about quantum gates, and specifically, what are some metrics that can tell us about the quality of the quantum hardware and the quantum gates that we're using. So, as it turns out, quantum control is actually very hard. If we think about classical computing, most of our operations involve flipping bits from 0 to 1, and everything is very discrete there. There's usually a transistor that's either charged up or not, and things are straightforward. There are actually not that many errors in classical gates. However, in quantum computing, there are a continuous set of possible positions on the Bloch sphere. So for example, if I start from the 0 state all the way up, and I want to apply a gate that takes me to the 1 state, of course, the full gate does this, but, I can overshoot or undershoot slightly or go left and right, and I will be off just a little bit. But, that little bit's actually enough to cause problem when we apply quantum operations many, many, many times. So since there are a continuous set of possible positions that I can be on a Bloch sphere, instead of just on the North Pole or the South Pole, that creates a lot of room for error. So again, that is the main source of error in quantum gates are these coherent controls, meaning that we're not making it just right to the point that we want to, but we might be a little off. Now, the way that we quantify how good our quantum gate is using a notion called fidelity. So a perfect gate will have a fidelity of 1 or 100%. And in general, fidelity is going to be equal to 1 minus the error rate. So basically tells us, how good our gates are. And it is related to the error rate using this relation. Now, of course, how do we measure the gate fidelity? Well, that's actually an active area of research. There are different ways to assess the fidelity of, of these gates to come up with a single number, and there are different metrics to look at. But something that I want to talk to you about today, and hopefully this will give you a rough idea of how we actually try to quantify this fidelity metric, or how good the quantum gate is, by talking about this protocol called randomized benchmarking, this method called randomized benchmarking. And it's actually not that bad after I explain it. So the name might sound a bit complicated, but it's very straightforward. So we start by initializing our qubit, let's say in the 0 state, DiVincenzo criteria number 2, we can initialize qubits fairly well, hopefully. And then let's say like the set of gates that we have, we were trying to benchmark, see how good our set of gates of, like, let's say H, T, and X are roughly. So what we'll do is that we will start applying random gates from this set. So I'll apply an H, then I'll apply an X, and then a T, and then dot. So I'll do a sequence of random gates. And then what I'll do, so this is the first part of the sequence. Now what I'll do in the second part of the sequence is that I'll start applying the inverse of each of those gates, or the complex conjugate. So for example, for this T, or and basically we're trying to cancel the circuit from side 1 and side 2. So for example, for this T, the complex conjugate is T dagger. For X, it's just another X gate. And for the Hadamard, of course, it's another Hadamard. So again, just as a review, Hadamard applied to Hadamard gives you identity. T and T dagger multiplied by T dagger gives you identity, and X multiplied by X also gives you the identity. And now the idea here is that, okay, so side 1, I just generated a random circuit, a random sequence of these gates that I'm trying to benchmark. And on side 2, I'm just applying the reverse. And then I measure. So let me see if I have a good poll for this. But if I measure, let's see, if I measure and I have, everything is perfect, let's do this. If I measure and all my operations are perfect, like we've talked about, am I going to get a 0 or not? So yes for 0, no for not. And let's fill this poll to see, what your thoughts are. Again, what I've done, to reiterate, is that I've applied a sequence of operations of these gates that I want to benchmark, see how good they are. And then I've applied the exact inverse. So what exactly cancels those gates on the other side? Okay, let's take another 10 minutes to get some answers in. And the question is, will I get a 0 on the other side when I measure or not? Will I get a 1? Okay, so yeah, I think that's pretty good. Yeah, so most people indicated that yes, I am going to get a 0 after I'm done measuring this sequence of operations. So this is if everything's ideal, but of course, if things aren't great, then what I'll see after I measure is that, okay, in this case, I think we're starting from, a 0. I'll see that the probability of measuring a 0 actually starts decreasing exponentially. And I can use this curve to figure out what the fidelity is. So now if I have this M being the number of gates, and maybe let me write this here, M is number of gates, then the curve that I'm trying to fit here is going to be some F to the power of M. And in this case, for the problem, for the sequence that I'm showing you here, the curve that fits this data the best I can actually take this data and see that my F is equal to 997 or 99.7%. So that's my gate fidelity. That's how good my gates are on average if I take from like a given set. So again, the idea here, just to recap, to figure out what is the fidelity, how good are some gates that I have, is to just apply a bunch of them and then apply the reverse of those bunch and see how close I get to the ideal case where I end up exactly where I started. And then I can use that as a metric, the probability of getting the desired outcome, and I can figure out what the fidelity is of those operations by just fitting f to the power of m, where m is the number of these operations. Now, of course, the way that it works is that I just make this circuit longer and longer and longer. And after some point, we see that we're very far from where we need to be, and that's an indication that at that point our circuit is no longer a good quantum circuit. Now, I have a question for you guys. So, does a 99.5% gate fidelity sound good? Yes or no? And I want to launch another poll where you tell me, if in your opinion, having a gate fidelity of 99.5% is good or not. And I'm going to try to find that poll. I found it. Okay, so yes if it's good, no if it's not. And with that gate fidelity, can I do quantum computing, essentially? Okay, let's take another 10 seconds. Okay, great. So a very slim majority actually indicated that yes, 99.5%, like if my gates are 99.5% accurate, that's pretty good. And from an engineering standpoint, that is really good. Actually, like if you think about it, if you're getting that close to your target state on the Bloch sphere, that is an amazing engineering feat. But now let's consider, if I have a quantum circuit, put 200 of these gates, then what happens? Well, so then the overall fidelity of the circuit is going to be equal to, I have, again, 995 to the power of 200, right? I'm applying 200 of these back to back to back to back to back. Well, so I did this math earlier today, and what I end up with is 0.367, yeah, or 36.7%. And that number doesn't look as good, right? It actually doesn't look amazing at all. In fact, for a good quantum circuit, we want the circuit fidelity to be larger than, larger than roughly 0.66, which is 66%, roughly. So although our gates are pretty decent, actually, from like if you look at them like at the first glance, when it comes to executing these quantum algorithms that we want, for example, think Grover Shores, where they're going to have actually thousands, if not millions, of these operations. All of a sudden, you see that 99.5% isn't quite enough. And in fact, maybe let's just, as an exercise, see what if we had 99.9% gate fidelity. or 0.99 or 99.9% fidelity. Well, then I did the math earlier, so I have 3 9s to the power of 200. Then my circuit will be, the circuit fidelity is going to be 81.9%. And again, for a, and this is where we see the impact of improving our gate fidelities, because by improving the gate fidelity by 0.4%, which again, might not be much for a single gate, we see that we go from an overall circuit fidelity that's really bad to an overall circuit fidelity that's okay. I mean, still, that being said, for a circuit that's has 1,000 gates, still 99.9% isn't good enough. And actually, that's why we need error correction at some point, because there's only so good that we can make these gates. And we need a way to correct for the errors that come up as a result of these gates. Now, I want to come back to this question of which processor is better. Now that we know a little bit about the metrics that we've talked about, specifically the average 2-qubit error and T1, T2 of each of these 5-qubit circuits, or 5-qubit processors, sorry. Can you tell me which one's better now? And let's see if y'all still think that the first one is the best one or not. Okay, let's give it 10 more seconds. Okay, great. So yeah, an overwhelming majority of you indicated that processor 3 or IBM Bogota is actually better than the other two. And in a sense, that should make sense now that we know about these metrics. For one, the average T1 and T2s on the qubits for Bogota are much larger, not much larger, but definitely larger than the other two processors. But also the average C0 error, which is a 2-qubit gate error, is much smaller, meaning that you have larger gate fidelities for Bogota compared to the other two processors. Now, of course, in this case, I've made the choice, deliberately simple for you guys by looking at 5-qubit processors that are all superconducting with similar gate times. When you consider processors of different sizes and different platforms and technologies, you need to take more metrics into consideration. But again, the metrics that we've discussed so far are a good first glance that the hardware community or the experimental physics community tend to report the quality of their quantum processor or their quantum hardware. So, for IBM, you can go and check all these numbers, compare them between the processors, and decide which one you like best. Although, of course, they use other benchmarking metrics like quantum volume, which we're not going to talk about today, but might be worth looking into if you're interested in. So maybe let me write quantum volume here with a question mark for those of you interested. And if you look at Google's processors, they report their T1, T2s and gate fidelity. So does IonQ. So does most of these quantum computing companies. So that's a good way, at least initially, to compare and contrast the different quantum hardware technologies that are out there. Now, again, that being said, there is the things that I discussed with you today, a lot of them involve an active area of research. For example, when it comes to decoherence and dephasing times. How can we improve those? How can we improve qubit relaxation times for different technologies? How can we perform better gates that have a higher fidelity or lower error? And also how can we quantify different errors that could happen when we're applying our quantum gates or quantum circuits? So with that, before we end the lecture, I would like to answer some more questions, and then we're free to leave.
I could pass along some more questions that have been coming up in the chat.
Yeah, that'd be amazing.
Also, I just wanted to make a quick plug for the lab. So we will be doing a very simplified version of randomized benchmarking in labs this week. So in case you guys are more curious about comparing different processors, we'll be comparing the Yorktown and the Belém processors, and we'll be looking at gate fidelities in both of them. And we'll get
and again,
similar curves.
Just to emphasize, that is an amazing exercise, because looking at gate fidelities and having an understanding of benchmarking techniques in general and extracting fidelities is a very important part of the research that's being actively done in improving these gates and these operations.
Okay, so passing along some questions. If you go to the last slide, Amir, which showed the layouts of the different processors.
Yes.
Could you repeat again, what is the significance of those different layouts? What does that mean, really?
Mm-hmm. That's an amazing question. So I think actually what they're asking rather is where or how does connectivity fall into this metric, right? Because when you look at the first processor, or IBM Q5 Yorktown, the qubits are better connected compared to Bogota, which they're all on a linear chain. So on the part of IBM, that was a deliberate design decision to actually have better gates, because in a sense, when you have less connectivity, there are less ways for your errors to propagate throughout your circuit. But on the other hand, it also becomes harder to do a gate between, for example, qubits 1 and 4. Because if you want to do a gate between 1 and 4 here, they're not directly connected. So it would have to go through 3 other qubits in order to be able to do that operation. And actually, no, that's why average C0 error rate or an average gate fidelity is in and of itself not enough. And that's why they look at quantum volume. And for quantum volume, basically what they do is that they compile a random circuit between all these qubits, and they look at what is the fidelity after they do all the operations needed for these circuits. And of course, the circuits that they compile have no idea about what the connectivity of the chip is. So the idea is that it will take your gate quality, your T1, your T2, and your connectivity into account in the final number that you get. And again, the way that I cheated a little bit in preparing this particular question is that the quantum volume metrics for these 3 processes are actually different. I think if I'm not mistaken, for IBM Yorktown, it's quantum volume 8. For IBM Belém is quantum volume 16, and from Bogota is quantum volume 32, although I might be off by a factor of 2 there somewhere. But the point is that there are more sophisticated benchmarking techniques for exactly figuring out which one of these processors are better.
Okay, and then another related question is, why aren't all of these errors identical? Like, why would IBM deliberately make some processors that are better than others?
Well, so actually, these processors, in a sense, they've been evolved throughout the time. So IBM Q5 Yorktown is one of the first processors, or one of the first designs that they made available publicly. And of course, Bogota is a part of their latest fleet of 5-qubit processors. So they were designed at different times. And actually, this goes to show how these T1, T2s and gate qualities have been improving throughout time, even at a single company.
Okay, then another common question was, so here it also says average readout error, and people wanted to know what that means.
Yeah, so that's a great question. I didn't talk about readout error that much, but the idea here is that, again, the fifth criteria, the fifth DiVincenzo criteria was figuring out or having, a good way to measure the outcome of our quantum computing. After the circuit's done, we want to measure the result of the circuit for our quantum algorithm. Now, this tells you, this average readout error tells you exactly, what is the error that you get when you do that readout. Like, for example, if you're expecting to get a 0, if your state is at a 0 and you get a 1 instead, that's a readout error. Or if you're initialized at a 1 and then you get a 0, that's a readout error. And this tells you, exactly, how much error do you expect? This turns out reading out a qubit is actually not, it's not trivial. Rather, there are modes for error, where you can essentially flip the state, accidentally read the wrong state. So you're supposed to get a 1, but you read a 0, and vice versa. And this just tells you exactly, what percentage probability does that happen.
And kind of building on that question, so if you're like an engineer and you're making these measurements, how do you know if the error that you saw was a C0 error or an average or a readout error or some other error?
Yeah, that's a great question, actually, Akshay, because this is what I do for a living, in a sense. So there are ways to isolate these errors, right? So, for example, for the readout error, what we do in lab is, we simply initialize our qubit to 0, then we do a bunch of measurements, and we see, what percentage zeros did we get? It should be ideally 100%, but that is not the case usually. Or, we initialize a qubit to a 1, and then, we measure and we see, with what percentage of probability did we end up getting a 1? Again, ideally 100%, but not usually the case. And based on that, we can calculate what the average readout error is. Now, for gate fidelity, let me maybe go back to our randomized benchmarking. So, if we have readout error for calculating our gate fidelity, what happens is that first point where we're applying 0 gates might be a little bit off because there's some readout fidelity, but that's not going to impact the exponential decay that we see. So, this F here, there might be some coefficient in front now, and, ideally 1, but, could be less than, could be less than 1 with errors. And that's fine, because that doesn't change how we extract this F, which is the base of this exponential decay. And that's the beauty of it. So you can have less than perfect readout, but you will still be able to extract your gate fidelities accurately. And it's the same with T1 and T2, if I can go back. Same with T1 and T2, because what matters here is this decay function, which is, in the case of, let's say, T1 maybe, T2 is a little bit more complicated. But in the case of T1, it's just this exponential decay time. Again, that is irrespective of, what coefficient goes here, but rather, it actually depends on the full exponential. So this is how you can isolate the way that you calculate each, or the way that you extract each of these error modes from each other. Otherwise, we would have been in great trouble. Maybe let me close this now.
Cool. And then going back to T1 and T2, since you mentioned them, could you repeat, because we talked about many different terms like relaxation, dephasing, decoherence. So could you repeat, what is the difference between these three, and what is the difference between T1 and T2 and T5?
Yeah, that's a great question. So in general, okay, so T1 is associated with qubit relaxation, and that's when your qubit drops from the excited state, which is 1, the state with a higher energy, to 0. Again, the good example for that is your coffee getting cold. So that is what T1 and relaxation time is. Now, when we talk about decoherence time, that takes two contributions. One of them is from your T1 again. So, if there's no noise in the world, your qubit will decohere because it relaxes. And it also takes another contribution from the dephasing rate, which is your environment messing with your qubit. And that is a difference between dephasing time and decoherence time. So dephasing time impacts decoherence time, but it's not the only factor that impacts the decoherence time. Rather, you also see an impact from relaxation. And that's all there is to it, pretty much.
Would one way of thinking about it be, and this might be, a bit rough, but would one way of thinking about it be if you think of a qubit as like a vector on a Bloch sphere, then relaxation is basically measuring the latitude, and it's measuring the time that it takes for that to change, and then dephasing is measuring the longitude, like along the kind of along the equator.
That's a great point, actually. So yeah, maybe let me transfer that have a Bloch sphere somewhere to play with. Okay, let me add a slide here, maybe, since I'm in this mode. Let's do insert new slide down here. And let's go in. So yeah, these are usually the stuff that I try to do ahead of time, but let's around some questions here. Let's do slideshow from current slide. Okay, so so again, if you have the Bloch sphere, right, you have access to the full thing in the presence of no noise. You have 0 on top, 1 on the bottom. Now, what happens with relaxation is that, and this is the equator, your Bloch sphere gets shrunk away from 1. So your effective Bloch sphere area will look something like this instead of the full sphere. So now the closest you can get to 1 is here. Of course, your 0 will be 0, but in a sense, your Bloch sphere is getting squished in the vertical direction. It's getting squished this way. Now, what happens with decoherence is that, again, you start with the perfect Bloch sphere, 0, 1, oops, and then dot, 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 this is the equator, and there's a line that connects 0, 1, and now your Bloch sphere kind of gets squished along the diameter. So, your Bloch sphere gets essentially slimmed down. And if there's any better way you have of describing this, please feel free to. But again, the difference is, one of them in relaxation, you get squished between 0 and 1. And then in decoherence, your Bloch sphere gets squished like along the radius, essentially, along like this direction.
So in a way, it's like restricting the possible states that your qubit can be in.
Exactly. It restricts the possible quantum states that you can be in.
Okay.
Because again, when we talk about these quantum operations, we assume that they're unitary and everything's on the surface of the Bloch sphere. But because of relaxation and decoherence, you actually lose access to the surface. And the stronger these are, the further you'll get from the surface.
And because a few people were asking in the chat, so both of these occur because of the environment. Would that be true to say?
Yeah, pretty much. I mean, so relaxation, I mean, both of these are natural processes. And again, like they come from the fact that your qubits are not isolated systems. They interact, they're usually surrounded by something, right? So in the case of a superconducting processor, for example, they're printed on a chip. Or, in the case of, for example, photonic quantum computing, they're usually like, in these silicon photonic rails. So they're usually interacting with something. And that is, that interaction, the fact that they're surrounded by something, that is a loss mechanism or a source of error.
Okay. And then a few people had suggestions on like how to maybe increase the relaxation and decoherence times. So people were asking, for example, suppose you were to dig a deep trench into the earth and put your quantum computer down there so that there's no cosmic rays coming in. Could
Yeah,
that
yeah.
help?
Yeah, I
Or
mean, that was actually like the press release around the work that we did, some in the press release, some people suggested, yeah, I guess, we need to take quantum computers like, like down under mountains or somewhere where they're shielded from the cosmic rays. And of course, that is a possibility, but, as human beings, we're smart engineers. So, it might be easier to think of engineering smarter like systems or like smarter environment that encloses these quantum bits such that they can do the shielding instead of digging a hole underground. But that is true. That is one way that people try to fight these. In fact, there was an article that came out a couple of months, maybe 2-3 months after we published our work that pretty much did that. They effectively went underground or under these mountains, and then they completely shielded off cosmic rays, and they saw the effects.
cool. And then one final question. So does the T2 and T1 also affect gate fidelity? Like, is there a relation between them?
Yeah, absolutely. So what I talked about mostly when it comes to gate fidelity, was coherent errors, meaning errors that come due to quantum control. But of course, decoherence also plays a large role. Now, with where we are today, just given the standard decoherence time and gate lengths, our gates are not limited by decoherence, but rather from coherent control, or rather the quantum control that we exert. That being said, if we ever manage to engineer the perfect quantum gate, meaning that we have perfect quantum control over how things move on the Bloch sphere, then yes, decoherence and relaxation will play a role in limiting our gate fidelities. I think the number right now, or the number that's roughly estimated, is around like 99.9% for 2-qubit gates. For superconducting qubits is where they'll start being coherence limited, meaning that they'll start seeing the effects of relaxation and decoherence in their gate fidelity.
And sorry, one more question that I forgot about. So could you give us some more numbers? So we've been talking about decoherence, we've been talking about gate fidelity. So could you give us some numbers about what are currently achievable decoherence times, fidelities? How long does it take for one gate to operate usually?
Yeah, so we are going to be talking more about that next lecture because it differs from technology to technology. But what I can tell you, the numbers for superconducting qubits right now are, let me maybe go back. So for single qubit gates, yeah, they usually take about, and again, this will of course differ from processor to processor, from company to company, or from lab to lab, but roughly around let's say 10 nanoseconds, maybe even up to 20, 30, and the fidelities that we can achieve are 99.99. That's been demonstrated, 4 nines. So, and this is superconducting, by the way. So single qubit gates are relatively easy. Now things get a little bit harder when we talk about 2-qubit gates. So think like C0, control phase, C phase, all those. These could take anywhere between 10 nanosecond to, let's say, 200 nanoseconds roughly. And of course, there have been limited instances where people have shown these fidelities to go as high as 99.9%. in one-off experiments, but generally for the quantum processors with many qubits available today, they're sitting somewhere around, I wouldn't say, between 99 to 99.5% roughly on processor. Now, T1s and T2s are, roughly of order of 100 nanoseconds. Or sorry, 100 microseconds. for, again, for quantum processors that are commercially available today. That being said, again, certain labs have engineered qubits, single or 2 qubits, or systems with 1 or 2 qubits that, have T1s and T2s of 1 millisecond. That was the most recent work that came out less than a month ago, or about a month ago. But we have yet to, of course, expand that to, again, a large quantum processor. So these are the rough numbers for superconducting qubits. Again, I will repeat them during the next lecture when we talk about this in more detail. But these numbers will be different from technology to technology and from platform to platform.
Cool. I think that's all the common questions we have.
Okay, amazing. Thank you so much, Akshay. Again, great questions, everyone. I'm very excited for next lecture. I hope you are too. We'll see some like what actually these quantum hardwares look like, and what are different technologies that are being considered and used for quantum computing today. So again, thank you, everyone. Thank you, everyone, and I hope you have a nice Sunday afternoon. Take care.